All right, next up is question 3. It says, sketch each curve by eliminating the parameter. Indicate with an arrow the direction in which the curve is traced as t increases. So here we have that x is equal to negative 3t and y is equal to 2t plus 1, and t varies from negative infinity to infinity. So here I first want to just point out that both x and y are linear functions of t. And for x, we're looking at a line through the origin with slope negative 3. And for y, we have a line with y-intercept 0, 1 and a slope of 2. All right. Now, if I want to eliminate the parameter, okay, I'm going to go ahead and solve for t in the equation for x. And that gives us that t is negative x over 3. And then I'm going to substitute in this expression for t in the equation for y. And we get that after some simplifying, y is negative 2/3 x plus 1. Okay, and this is the equation of a line with y-intercept 0, 1 and a slope of negative 2/3. You see that here in red. All right, now as far as the arrows which indicate the direction in which the curve is traced as t increases, well, go back up here and note that as t increases, x decreases and y increases. So what that implies for this graph down here in the xy plane is that, well, we'll be moving to the left since x is decreasing, and we'll be moving up since y is increasing. So we conclude that as t increases, we'll be moving along this red line in the direction indicated by these arrows. Cool. All right, so that does it for part A. Let's check out part B. And for part B, we have that x is equal to the sine squared of t and y is equal to cosine squared of t. And here, t varies from 0 to pi. All right, so just like in part A, I'll start by just sketching the graphs of x and y versus t individually. So since x is sine squared of t, it's going to start here at 0, then increase to a maximum value of 1 when t is pi over 2, and then it's going to decrease back to 0 when t is pi. For y, since it's cosine squared of t, it's going to start up here at 1, decrease to 0 when t is pi over 2, and then increase back up to 1 when t is pi. All right, now as far as eliminating the parameter, I'm going to not want to solve for t in either one of these equations in this case. And the reason why is because I'm going to have to deal with an inverse trig function. And you can see from these graphs, neither x nor y are one-to-one functions of t. Okay, so to solve for t, you're going to have to split things up and consider two different cases because of the non-one-to-oneness here. You have to break things up at pi over 2 in this case. I'd rather not do that. Unfortunately, there's a much easier way to proceed. Okay, the idea is to go back to the Pythagorean identity from pre-calculus. Right? We know that sine squared of t plus cosine squared of t is equal to 1 for all values of t. And see here, since sine squared of t is equal to x and cosine squared of t is equal to y, this condition implies that x plus y is equal to 1. All right, so this is the equation of a line in the xy plane. And so to better understand where we're going to be located on this line at various values of t, I'm going to go ahead and just plug in a few values of t. Let's go ahead and do that here. So when t is 0, just plugging in, we get that x is 0 and y is 1. So we're located up here at the point 0, 1 when t is 0. Now letting t increase to pi over 2, okay, we see plugging in that x is 1 at pi over 2 and y is 0 at pi over 2. So we're going to be right here on the x-axis when t is pi over 2. And how are we getting from this point to this point? Well, we're moving along this line, right? So we're tracing out just this portion of this line segment in this direction as we let t increase from 0 to pi over 2. All right, now, as we let t increase from pi over 2 to pi, what's going to happen? Well, at pi, plugging in, we get that x is 0 and y is 1. Well, that was our starting point, right? And see, we can go back to the graphs up here. From pi over 2 to pi, x decreases back to 0, saying we're going to move to the left, back to 0. And y is going to increase back up to 1, saying that we're going to move vertically upwards, right, 1 unit. So we're going to, in other words, retrace this line segment just in the opposite direction, and we're going to wind up right back where we started when t is pi. All right, now real quick here on Desmos, can animate this. I put in the parametric equations, and then here is my tracing point. And so as I let a increase from 0 to pi, let's see what happens. Hit play, go down, and then we return back to where we started. Okay, so here we are at pi over 2, we turn around and then retrace. All right, very nice. Let's then go ahead and check out part C. Here we have that we have the set of all ordered pairs, r cosine t, comma r sine t, where t varies from 0 to 2 pi. And so this is telling us, right, that the x coordinate of the ordered pair, right, x is r cosine t and y is r sine t. I've just included their graphs here. And as far as eliminating the parameter, well, much like part B, since I see cosine and sine here, I'm going to make use of this Pythagorean identity, and that's going to, again, allow me to avoid having to consider an inverse trig function. All right, so cosine squared of t plus sine squared of t is equal to 1 for all t. And now the thing to note here, for cosine squared of t, well, we know that x is r cosine of t, right? So what is cosine of t? It is x over r. And so cosine squared of t, that's going to be x over r squared. Likewise, for sine squared of t, well, sine of t would be y over r, and then I'm squaring because of the square on the sine. All right, so this condition here implies that x over r quantity squared plus y over r quantity squared is equal to 1. And multiplying both sides of this equation by r squared tells us that x squared plus y squared is equal to r squared. Okay, so now this is the equation of a circle of radius r centered at the origin. Okay, so I'm going to go ahead and plot points on this circle, and to better understand where we are on the circle for various values of t, just like in part B, I'm going to go ahead and just plot a couple of those here. All right, so if I plug in these values, so 0, pi over 2, pi, 3 pi over 2, and 2 pi, okay, we get these different values for x and y. And so we're moving along this circle of radius r centered at the origin. When t is 0, okay, x is equal to r and y is 0. So we start right here on the x-axis when t is 0. As t increases from 0 to pi over 2, well, at pi over 2, x is 0 and y is r. So we've moved to the top of the circle here in a counterclockwise fashion. So we're at 0r when t is pi over 2. And then we can see we just continue, right, and we make one complete trip in 2 pi units. Now here, you can think about t as denoting time, and we're just tracking, say, the motion of a particle. But we could also think about t as the central angle. If I consider a point on the circle, right, just like you see in pre-calculus, right, if I draw this little right triangle here, right, the angle formed by this ray in the positive x-axis is typically denoted by theta, and that's what you often use in pre-calculus, but that's really what this parameter t is telling us in this context. All right, cool. So here I'll go to a graph there to illustrate. So r, right, that just controls the radius of the circle. And then 0 to 2 pi units, we make one full trip around. And as you can see here, it appears that the particle moves with constant speed, and that is in fact the case. This is what's known as uniform circular motion, and we'll get into that in more detail. We start talking about vector functions later in the quarter. All right, but that's a good place to stop here. I will see you in the next video. Thanks so much.